Good afternoon, everybody. I don't want to try to start my talk in Russian, because I only know one word in Russian, that is canalia. Usually people laugh. Yes, exactly, okay. So it's good. So welcome to this presentation about mutation testing at scale. Let me spend 30 seconds on myself. I am a software development manager in Amazon. I lead the Kindle rendering team. So every time that you open a book and you read a book, you can blame it me if the page doesn't look exactly how you want. I am organizer of the DroidCon Boston, maybe Seattle, Swift Boston and Atlanta. It's another vertical conference on iOS. I'm pretty enthusiastic about communities, about meetups. I travel not for work, I travel for pleasure, speaking, meeting people, and that's why I'm here. And I want to thank the staff of Mobius for having me here and for this great conference. On top of that, I lead the system architecture and design learning track in Amazon, so I spend my time, my spare free time, also in doing this for Amazon. Let's get started. So let's start with the first concept. We are talking about mutation testing, right? So we want to understand a little bit more about software quality, and we want to be sure that we are on the same page. Quality starts with clean code. How many of you can claim that you're writing clean code? I'm arrogant enough to say that I can write clean code. Quality, it's very important. Clean code is not that complicated. Just let's take a look to this slide. Which is the difference between these two lines of code? Nothing. Except that if you read the second one, you will remember what it is. If you read the first one, you will blame forever who is the guy that wrote that line. When you want to measure code quality, you should take a look to the reaction and the amount of comment during code reviews. There is a metric that we try to use that is the what the fuck per minute. It's usually work. Good code, it's pretty clean. The good part about clean code is that clean code, it's testable. And every time that you add a test, you are cleaning the code. Why? Because adding tests shouldn't be complicated. Adding tests should be extremely straightforward and should always remember us that our code must be complex, but not complicated. There is a big difference between these two words. Complex for me is good because it's interesting. Complicated means that there is something that is not working as expected. Are you doing TDD rigorously? In my team, we tend to be extremely rigorous. We don't write a test after we fix a bug. We write first the test that proves that the bug exists, and then we fix it. Tests are first-class citizens. Tests are code. Code should be of high quality, and tests should be of high quality as well. The anatomy of a good test should be that it's self-descriptive, it's simple, and it's solid. There is a reason why the L is dashed. By solid, what I mean to refer to the single responsibility principle, open for modification, the least scope substitution principle, and so on. The only one that really doesn't apply to test, it's exactly the least scope substitution principles. But everything else should be the same. For instance, what do you want to test here? So this is a very simple method, function, that returns you the tail of a string. Here you should at least test for three things. That all the letters after the head are part of the tail, that an empty string should have an empty tail, and then a string with at least a single character, only a single character, should have an empty tail as well. These tests are simple. They're not complicated. You can look at them anytime, and that is an example of your code in exercise. But what is a good test suite? So a test suite should be reliable. How many of you retry test after a build? To me, it happens several times, yeah? We have someone. Reliability, it's very important, should be accurate, should give you the right information, the right location of where your tests are failing, and potentially also some more information than just the assertion, and should be fast. What is the average time that you wait for your test? Who waits more than 10 minutes? Okay, more than 1 hour? More than 3 hours. So, I know I shouldn't say that a test suite is fast and then say that it takes 3 hours, but what I do, it's the rendering engine of Kindle. Imagine that it's like building a browser, but it's specific for books. So it's a lot of tests. And we reduced the length of test from 4.5 hours to 3 hours in the past month. So it's always something that we should take care of. Which are the potential quality metrics that you want to apply to a test suite to see if the test suite is really effective? One can be the line coverage. How many line of code your test suite covers? Another one is reliability. There was someone that raised the hand when we were talking about tests that can fail and you retry. And another one, execution speed. In your mind, which one should be the most appropriate? Guess? Usually, this is the answer. All of them. But that's not really the truth. Because we should automate the quality checks that we apply on our test suite. First of all, we should ask ourselves if it's beneficial adding tests. What do you think? Adding more tests help the reliability or the effectiveness of your test suite? Yes or no? Who said yes? Who said no? Okay. I will prove you that the no is right and the yes is wrong. Why? Because it depends which test you add. There are tests that don't add any value to any test suite, that are not proving anything, and sometimes line coverage can be just a false impression of being covered by something. For instance, again, the right test coverage, that's an interesting topic. There are teams that claim that they have 80% of test coverage, teams that are happy with 10% of test coverage. I found myself once reviewing the app that a contractor delivered to McGraw-Hill Education, a company I was working years ago. And he claimed that it's 100% test covered. And the stats were proving that. Well, the only test that was running was a test about around the initialization of the app itself. So, of course, the coverage was 100%, but the effectiveness was about 0. Let's look again at the test that we wrote before. By any chance, any of you notice that here there is not a single assertion? This is just executing the method. Well, basically here what is happening is that you are 100% test covered, but you're not testing anything. The other big important problem that test coverage doesn't solve is the oracle problem. What is an oracle in TDD? It's the entity that decides if a test is passing or it's failing. In that situation, in the situation that we saw here, the tests are all passing, but there is clearly some problem that nobody can check except if you want to do a code review, but you can miss it also in the code review. How many of you look at the codes during at the test during the code review? Okay, that's very good. So you look at you look with the same eye that code, usually a little bit of less attention. And things like that can pass. So let's see how we can approach the problem differently. First of all, we can learn from earlier mistakes and prevent them from happening again. So we can have whatever script, whatever check that you want, whatever automation that control that every test has an assertion. Or we can simulate earlier mistakes and see whether these results are discovered by our test suite. This is basically fault-based testing. So instead of looking at the test just as a success, you look at where the tests are failing or how tests failed before. And by failed, that doesn't mean just that the test was read. The test failed to prevent whatever bug that is in production. and you flip the coin and you start to look at fault-based testing. Because not every time things are black or white. Zebra exists, and that's a proof. Let's start talking about fuzzing. Fuzzing is a technique that is able to measure the degree to which a system, component, or function can work with an invalid or stressful input. Basically, with fuzzing, you deviate from the normal expected flow of a program, and you test, and you check how it is going and if the program is able to handle this failure. For instance, look at this code. This is nothing more than a function that checks if it's an even or odd number, and a validation that we can apply before using this check even odd function. The validation check and control if there are 0 and 9s. Basically, if we have numbers into whatever input it is. But that's not enough. It's yet pretty open. This is a simple validation that doesn't guarantee that your code is getting executed correctly. There is anyone that is familiar with the hurt bleed bug? Yeah, 2. Okay, let me tell you the story for the others. So everybody is familiar with OpenSSL, right? Yes. So OpenSSL, it's a security layer that connects different components of different applications, and it's especially tailored for web. There is an extension inside OpenSSL that is known as Heartbeat. The Heartbeat extension was pinging different servers to keep the connection live. The method was pretty simple. You pass a string, you pass an integer that say how long is the string, and then you check that the result is exactly the same string. Basically, it's just a ping pong that returns you the same message. The problem is that whatever string you pass, it doesn't matter, because you can pass an arbitrary integer as the buffer length. And then what happens is that you go in buffer overflow in the other server, and you recover everything that you want. Basically, when the bug was discovered, you were able to recover passwords, certificates, all the sensitive information of other server. For this reason, from the Heartbeat service, we found this funny name that is Heartbleed, because information were bleeding in whoever was able to spoil and to sniff which was the method to call to keep the other servers alive. If you apply fuzzing, you will spot for sure issues like this. So you can find early bugs, you can discover security issue, and you can discover which are the fragile areas of your code base. How you can do this? There are mainly 2 approaches, dumb and intelligent fuzzer. Dumb fuzzer, they don't do anything more than mutating the input, the expected input that are also in test. And they create very long string, numbers, whatever is the input. Intelligent fuzzer, instead, they understand the file format protocol, and they do a little bit more. They generate input from scratch based on the specification, so are a little bit more sophisticated. Both of them have some drawbacks. Fuzz testing cannot provide a complete picture of the security threat or bugs that you have in your code. And fuzz testing can only detect simple faults or threats. If you want to really perform an effectively and significant set of tests with fuzzing, we will have to consume a lot of time. It's not fast at all. Last but not least, you are setting the boundary of a value condition with random inputs. And that's very problematic. Basically, you are trying to determine which are the boundaries that you have to test your application with random numbers. And that's then not easy to analyze, to make decisions, and to understand what is really the boundaries that you have to test. There are several tools. There are fuzzing frameworks like BuFuzz, BDFuzz, mutation fuzzers that are simpler but very effective, AFL, libfuzzer, and Radamsa. AFL, it's one of my favorite because it's a standalone tool and it uses binaries to rewriting the instrument that the code, to instrument the code that have to be tested. So it's pretty independent and you can use it with a lot of languages and a lot of tools. What's the problem with fuzzing? Fuzzing doesn't listen. So whatever you're doing, whatever input you're sending, whatever, you can verify things, but you cannot improve, never. And that's why mutation testing came into the picture. But let's take a look to a simple animation that can expect, yes, that's an expected program mutation, right? It's clearly. So with mutation testing, you can spot problems like this. You can see how your program can mutate and how your test can fail in checking the mutation. Let's take a look. Let's start to dive deep into it. So with mutation testing, you evaluate the quality of the test. And that's a different approach. Rather than start saying that I'm 100% test covered, you are understanding if the average coverage that you have is good enough and it's spotting the real problems, the potential problems that can happen in your code. The idea is to modify, that means mutate, the code covered by the test in a small way, in a very minimal way. Maybe flipping a value, maybe returning 0 instead of 1, or maybe switching a plus with a minus, whatever minimum modification. And then detect if the tests are detecting or rejecting the change. What does it mean? It means that if the test still pass, then there is a problem. The problem can be in the test, and sometimes can be also in the way that the source code is organized or designed. There are several mutation testing frameworks, and we'll take a look to several today. What they do, they alter the source code in a very small way. They run the unit test against this altered program, and they record if a test fails. Before talking about mutants, let me emphasize one thing. They record the test that fails. It means that you have the data. So with fuzzing, you have random input, and you see some failures. With TDD, you have maybe, if you have a good test suite, you have a track of how the tests are going. But honestly speaking, when everything is green, nobody look at this data. Mutation framework record this data and keep this data in a DB or in a JSON file. You can decide what is your output. This means that you have an history and that you can analyze this data and learn a lot from that. A mutant, it's a transformation that happens from the source code. Basically, every time that this source code is changed by a little tiny bit, you have a mutant. One important thing is that mutation can happen at the source code or at the binary code. Basically, you can mutate the binary through bytecode, or you can mutate the source code. Detecting and rejecting such modification means that you are killing a mutant. Killing a mutant is nothing more than that. You are going to see if the mutant can be detected by your test or not. And then you collect a lot of metrics. These metrics are made with several data points. One, it's the mutation score. Another one that is pretty important is the time that you need to build and to run every mutant. You can make analysis on junk, on equivalent mutations, and so on. All these metrics give you the opportunity to measure the effectiveness of your test suite, because the effectiveness is the ability to detect the mutants and not anymore how lines of code are you covering. The mutation score is the ratio of killed mutants to the total numbers of mutants. Okay, who said that test coverage was a good metrics? I don't see any more hands. So it's important, test coverage, don't get me wrong. But if the tests are not good, why we're testing? And if you have the opportunity to work in a successful project, and you see your project scaling, and you start to have new developers will add tests, starting from the original test. And if the original tests are not that great, you are simply creating a not realistic representation of the quality of your product. That's when mutation testing comes into play. You can have different mutations. You can have statement mutations. That means that the mutation framework can cut and paste part of the code wherever wherever it wants. You can have value mutation that is pretty intuitive. Decision mutation that it's changing the operator that make a condition true or false, and so on. Statement mutation. This is pretty brutal. So instead of having c equal 10, you have different variables that get assigned these values. And then you see how things go. Value mutation, pretty simple. You see that in the mutated code, you have significant smaller numbers, for instance. And this can cause unexpected behavior. A small value is changed to a larger value and vice versa, and you analyze how it's going and what is going on in your code. Decision mutation. This is one of my favorites. Basically, these small changes sometimes can be extremely surpriseful. I found, for instance, and you will see a slide in a little bit, that switching a plus with a minus doesn't make the test failing in a pretty popular C++ library. And that's interesting. With mutation testing, you have a lot of mutations that are at an operator level. Meaning, for instance, that you have an arithmetic operator replacement. The arithmetic operator replacement basically change the modulo division, and this can be replaced with plus, minus, multiply, whatever. And that obviously will create a problem. This is a function that check and return to you the greatest common denominator of two numbers. If you change this, all the math will go away. A relational operator replacement. The different operator can be replaced with less than, greater than, and all the other operators. Also in this situation, with the relational operator replacement, you can dramatically change the way your code gets executed. Conditional operator replacement. These are all the mutations that the most common mutation framework can apply and to your code or to your source code. Many others. There are assignment operator replacement, unary operator insertion, scalar value replacement, absolute value insertion, and even more. There are a lot of operators that change the way your access modifier are defined in classes, how an overridden method gets renamed, and all things that should create failures in your test. And I want to emphasize the should. So mutation testing, you flip the coin, you have a different approach, you start to identify areas of code that are not tested properly. And that's different. It's easy to understand which are the areas that are not tested. You have line coverage, but you are not sure which are not tested properly. Another important thing is that you can identify hidden defects. And these defects usually are not caught by QA, because QA will never input whatever random value, will never do these kind of operations. Another important thing is that you assess continuously the quality of the tests that are part of your test suite and that get added. So you can save time at code review, because if the mutation testing is passing and you have a good mutation score, nothing is getting broken, you can also spend more time looking at the code rather than the test. Another interesting thing that you can do is assessing the error propagation. So you can have infinite loops, runtime error, you can have everything when you mutate so dramatically a component in your code base. And you can see how how your software is handling the propagation of these errors. So, mutation testing works very well with mutation analysis. Once you run this test, with these frameworks, you get this data, you should start to do an analysis. There are several papers that I would recommend to read. How mutation analysis is changing the way that mutators and mutations are generated inside every single framework. One of the big problems with this technique is that not it doesn't work, it's that it's slow. Imagine that if you run a simple, whatever, let's talk about FMT, that is a C++ library to format your output. If you run mutation testing on that, it creates 409 mutants. To run the test or the entire test suite around on top of these mutants, it takes time. So through mutation analysis and to analyzing your data, you can understand how you can fine-tune the generation of mutants to fit your needs and to improve your performance. And trust me, there are a lot of data. I will show you some examples. Let's start to talk a little bit about mutation testing on LLVM. How many C++ developers I have? Yes, thank you. Thanks. Okay, so LLVM, it's not an acronym, it's the name of the project. It's not a virtual machine. It's a very low-level framework to build to create binaries, and it supports several languages. The supported languages for mutation testing, it's a lot. There is Java, the JVM, so Kotlin can be used with mutation test, PHP, Rust, C++, Clojure, JavaScript, Scala, Swift. And let's focus on Rust, C++, and Swift. Why? Because all of them can be built with the LLVM. So through the LLVM, you can have a lot of fun with the low-level representation of your code. You can access to the just-in-time compiler. You can access to the IR representation of your code that is very close to machine code, but it's much more readable. So you can still understand something. And again, it's able to compile C, C++, Rust, Swift. And if you are brave, you can use LLVM as your front end to develop a new language. So a lot of languages born like this. There are several available tools that can work with LLVM. One is DexTool Mutate. DexTool has a very interesting feature for me, that it can continue from where a testing session was interrupted. So whenever a mutant gets detected, survive, you can pause everything and you can start again to run the test from there. MuCPP, it's based on source code mutants generation. I don't recommend using mutation framework that are based on source code mutation, because it means that every time you have to recompile everything. So accordingly to how much time it takes to compile your code, then it can be extremely painful. There is Mule. Mule is LLVM based. It has a strong focus on C and C++. It's the tool that I'm more engaged at the moment, especially because, again, as I said, my job is mainly in this rendering engine of the Kindle. So that's why I'm so interested into this side of the, let's say, in the dark side of the C and C++. There is CC Mutator. CC Mutator, it's based on high-order mutation. If I remember correctly, this is not anymore updated since several years. And XEMU, it's based on QEMU, basically use emulated environments to run mutation testing. That I think it's an interesting approach. But again, for me, it was a little bit overkilling. So let's talk about Mule. Again, it's open source. It's based on LLVM. It's very extendable because every time that you want to add a support for a custom test suite, you just extend the test suite, the existing test suite, and you can leverage whatever need you have. And as a very interesting and powerful command line tool, basically every time that you want to start to work with Mule, the first thing that you do is you build it. Once you build it, you have a command line tool that is Mule CXX that it's extremely powerful, well documented, can help you to pass whatever information and whatever parameters you want. For instance, here we're saying that we want to use Google Test as a test framework, that we want to use conditional mutations, meaning that we want to change the condition, we want to flip the true and the false, that we want to have a report not on a DB, but on a JSON file with an HTML wrapper, that we want the report into this directory. We want this name, we want to allocate 4 threads to execute the mutation testing framework, and that we are passing these compile commands. Basically, this is the path to the DB. It's also creating behind the scene a SQLite database. You don't want to use, you want to use the cache. You definitely want to use the cache. And this is where you are using the binary that you want to execute to run all your tests. So easy to run, easy to configure, and it's extremely efficient in generating the mutation because it directly manipulates the LLVM IR code and support dry run mode. Dry run mode is very interesting. Instead of executing the entire test suite, it basically just creates the mutants and collect information about all the mutants without running all the tests. As a very effective sandbox model, obviously software can crash, right, during the mutation testing. Every process is sandboxed and there is no big risk for the system that is running the framework. As a flag that you can pass to the command line tool that will fail fast, meaning that as soon as it gets the first mutant that is passing the test, it will stop the execution, so you can focus on the first problem that you find rather than on the entire set of problems. And has a lot of interesting mutators. As mathematical mutators, basically addition, subtraction, multiplication, division can be flipped between each other, conditional generator, everything that is less than, greater than, equal can be flipped. Remove void function. This is one of my favorites. Basically, every time that it finds a function that is void, it doesn't return anything. It just removes the execution of this function from the function that is under test. Replace call, obviously, you can replace call and you can return a floating or an integer, an arbitrary value, and you can see how your software behave, and you can replace any scalar value. Many others. If you just run mule cxx-help, you see the list of all the mutators. Let me see if I can show you. Yes, that's the list of the mutators, just to give you an idea of the flexibility that you have in your hands. What's the approach of Mule? First of all, the first thing that happens, Mule started to so Mule it's an interesting approach because first thing is that can be done at high level or at lower level, and Mule relies on bitcode. It relies on bitcodes because the same engine can be used to support many LLVM-based language, and because the execution time is much, much lower. So every time that you mutate from source, it takes the time that usually an incremental compilation takes. Every time that you create a mutant from bitcode, it's maybe 15, 20 times faster. Under the hood, it loads the LLVM bit code into memory, inserts the instrumentation code in each function, then compiles the instrumented LLVM bit code and the machine code, prepares the machine code for execution by the JIT engine, and then at an higher code level, finds the matching test, runs each test against the JIT engine, and collects code coverage information. Drawbacks. Obviously, nothing is perfect, especially in mutation testing. Compiling with bitcode enabled, it's very straightforward for a small project. For a big project, it can take time. The reason is pretty simple. If you want to compile with bitcode enabled your project, you have to compile with bitcode enabled also all the dependencies. So be ready to spend some time in writing a Python script or whatever, or a CMake file that it's pretty smart enough to enable bitcode in all the dependencies. Mutation at bytecode generates noise because not all the mutations have a representation at code. So you have to spend some time in analyzing this data. Some mutations generate the same behavior, and you have to be good at spotting that. It's not a solution for black box testing. If you cannot recompile the source, you cannot use it. So you can ask why we're doing that. Well, there are several good reasons why. You are identifying potential area of improvement. You are finding bugs that are behind the human interaction. So you are doing a job that it's not doable with hand work, with the manual testing. And you are optimizing the error handling strategies in your code base. On top of that, you are estimating the remaining bugs, the remaining unknown bugs of a program. Yes, it's possible. You can absolutely determine how many bugs, roughly, it's an indication, are still existing in your code. Let's take a look at reports and metrics. So, I always advocate to discover, inspect, and improve your code. That means that every time that you generate a report, you have to take a careful look to what you're doing. For instance, we already went through all the details. We know now that I'm creating a report with the name test in a specific directory. And I also want to emphasize what is this. This is the binary that ran the test of FMT. FMT is an open source formatting library for C++. So it's a pretty simple project. And once you run it, you should start to explore the logs. So if you look carefully, I was right. It's just 409 mutants for a pretty small library. But it's very interesting looking through the logs that you have a lot of operations. You are removing original tests, you are applying function filter, you are searching mutant across functions. And this is very interesting because this number is the number that I decided to use. What do you get? You got this, for instance. On the core.h file of FMT, you have a mutation score of 33%. Basically, there are one mutant that got killed and 2 survived. So this is a clear indication that there is some problems. For instance, if you look at this function, you can see that when you replace minus with plus, the mutant survived. And this can open up a lot of debate on where and how to test it. So that's an indication. And then you have to go back into your test and into your code and see if both of them are correct. I want to emphasize that this took 21 seconds. So the first run with the cache disabled. So to simulate the first run, you have to disable the cache. With cache disabled, to create 400 mutants, it takes 21 seconds. Project and programs with a wider scale can take hours. But you can estimate the remaining bugs. Let me prove it. You can switch your perspective. You can count how many open bugs you have in your backlog. You can label or categorize 30% of them, and then you can run Mule. And then you can categorize and count the bugs. Basically, what you want to do, you want to understand in the bugs that Mule identified, how many of them were labeled from you, manually labeled. And then you calculate the ratio. So let's say that you have 300 known bugs, you have 100 labeled bugs, and you have 30 existing bugs discovered with mutation, but a total of 100 bugs discovered with mutation. Any guess how many bugs are in this code base? More than 100? No, more than 200. So don't panic. Every code base has a lot of unknown bugs. Bugs are there. You just don't know. You will discover. This can give you an idea, a representation of how bad is the situation. And then you can improve. Having a bug in your code base doesn't mean that your customer will discover it. Potentially, it will happen. So no panic, and keep the positive attitude. And start to see how you can scale mutation testing. Because so far we went into a path. We understood what it is, we understood the importance, we went deep into how Mule and why Mule, in my specific use case. But then there is a problem. If you are a team of 5, that's easy. You have a conversation, you go out for lunch, and everything is ready. What about if you have a team that is bigger? There are cultural changes that you have to first of all approach if you want to start to use mutation testing in your team. The first thing that you have to change is that code quality should be essential to release a successful product. We should switch our perspective. We're not talking anymore about source code. Whatever you compile, whatever you deploy on the web, no matter which is the platform that you want to use, it's a product. Someone is using it. Also for other developers. It's possible to objectively evaluate the code quality. So instead of using metrics like how many complaints, how many all-way conversation are blaming the code of the quality, with mutation testing you can absolutely be sure about the quality of test and the quality of code. Automating quality check, it's absolutely essential. You cannot think to do this verification manually in your own laptop and be successful. First of all, it's not the build environment. Second, it's time consuming. So you have to definitely automate this. You have to switch also your perspective on test. Tests are code, and you should implement tests with the same criteria of code. Technical challenges. Compilers. How many of you are on? So we have only 3 C++ developers. So let me ask a different question. How many of you are deploying only on the latest version of Android or iOS? Okay, nobody. How many of you have a build infrastructure that can support whatever version of iOS and Android? Okay. So same is for C++. Obsolete compilers are part of our life. I still have some projects that compile with C++ 11, and we're in 2019. Obsolete compilers can be absolutely updated. It's a lot of pain, but it happens. But you can go through it. The other technical challenge that you have to solve is that you want to integrate the checks in your build tools. You don't want to wait for you don't want to, again, have the situation where you have to manually do something. You want to have a check, you want to have a report right away. So no matter if you're using custom build pipelines or if you're using any open source solution, any commercial solution, you want to integrate this check in your build tools, and this will cost you. You have to learn how to minimize the junk that are in your data. A lot of mutation maybe equivalent mutation, maybe false positive. You have to learn and you have to track how these things change. You have to be able to support every operating system because you want to, in any case, have every of your engineers being able to run mutation testing in his or her own environment. So these are technical challenges that you have to solve. Compilers, again, they can be updated, but you can also start to review your software architecture and simplify the compiler's update. For instance, it happened to me once that we were updating the Visual Studio compilers of a specific set of products, and there was a pretty deep problem because we were forced to update all the dependencies. Well, we discovered that if instead of consuming the dependencies statically linked to the product, we were loading as DLL, well, then this problem went away. So we reviewed the architecture of the software, we started to consume dynamically loaded libraries, and in this situation, the architecture allowed us to proceed to speed up the update of all the other components. Remember that updates are like a fresh start. Every time that you update whatever compiler from whatever version to another, it's like a fresh start. There is a lot of pain at the beginning, but then everything else is fine. Pipeline integration. Every build infrastructure can integrate any tool. You have to spend time to integrate the mutation testing framework in your build infrastructure. Be thoughtful when trigger mutation testing, because mutation testing is time consuming. And if you start to trigger this, the mutation testing framework at every single commit or at every single commit or at every single code review, it will slow down you instead of improving the way you can code. One approach, for instance, is every time that there is a merge, you can trigger mutation testing, or every time that a code review is approved after there are the first round of comments. It's absolutely up to you and everything is configurable. Analyze your data early in the process and often. Modularize your pipeline. Be sure that you can trigger off mutation testing at any time, because otherwise you will risk to be in a situation when you are blocked or you are forced to wait for hours and hours. Dev environment. Invest time to simplify the usage of the tools that you're going to integrate. Mule can be distributed also as a binary. That's Simplify, for instance. LLVM thankfully already has binary and source code distribution. But whatever tool you're using or you're planning to use in your dev environment, be sure that whoever is joining your team is able to run it in a couple of hours. Be inclusive and support all the dev platforms. There are a lot of engineers that use Mac, some that use Linux, and several that use Windows. Be inclusive. Don't make them crying or hating you because you're not supporting a platform. Write exhaustive documentation. That's important because I don't want to join a team where I have to spend days to guess what is going on. I want precise documentation. Every time that you got a report, review the data in isolation and then share your findings with the rest of the team. It's very important that you spend time browsing the HTML report or the SQLite database and you understand what is going on under the hood. Filter the data, share the findings, and then once you collect the finding, learn from them. Learn from them means that you can also filter out from the data that you collect whatever you don't need. Implement a data model and learn from errors. That's one approach, one potential approach to speed up mutation testing. And once you have done all of this, get ready for a new challenge. You can scale mutation testing at any size team. So let's start to wrap up this presentation. The first thing is a fun fact. You got exposed to more than 20 new acronyms and you survived. Congratulations. After lunch, this is a big achievement. You get exposed to a lot of new ideas and a lot of new terminology. A fault is an erroneous part of a program. A mutation is a fault that introduced in a program. A mutant is a program created from the original one with a potential failure. A variant or a variation is a program that shows a deviation at runtime from the original program. And a redundant fault or equivalent mutation is a duplicated fault. You learned that we can run and we can use mutation testing basically on any programming language. One important thing that if you decided to dive deep into mutation testing, to understand that a lot of time you will get the word bitcode and sometimes the word bytecode. Bitcode, it's you are in the C++ world or in the LLVM world, and bytecode you are in the Java world. They are about the same but different because, for instance, the bytecode that is JVM based are stack oriented while LLVM is not. LLVM bitcode, it's closer to the machine level code and it's not bounded to any particular architecture. There are a lot of resources that you can start to explore. One about fuzzing is this Git repo that is maintained pretty often, and there are a lot of interesting papers, slides, presentation, and so on. The LLVM command line, because starting to use mutation testing, you will have you need to understand what is going on with LLVM. Mutation testing, again, on GitHub, there is a pretty well curated list of resources, and Rahul Gopinath, that is from the University of Oregon, has at least 5 publications that are related to mutation testing. An extremely interesting one, it's focused on how to improve performances on mutation testing and generation of mutants. That being said, thank you.
We still have time for questions, so please raise your hand.
Thank you for a great talk. I have basically 2 questions.
Sure.
First, how many bugs in your team, in your practice, have you found with this technique? And could you give some more concrete details? What was the nature of those bugs found?
Sure.
Thank you.
Let me think how to... great question, first of all. Let me think how I can share this information without compromising anything. So I would say that we found a good amount of bugs so that there was a significant improvement. And we found some issues around the 2 things happened. One was with the position of objects on the screen that were getting out of the visible area. We detected that. And another use case that I can tell you is that on very poorly formatted source files, and by source files I mean content, we found some other problems. So we had both words, a little bit of significant in the mutation testing world and something in the fuzzing world. You're welcome. Other questions?
Thank you, first of all. It was very interesting. Could you please tell how long does it take to run your mutation tests according to more than 3 hours usual test? Also, please tell about how often do you run this, and where did you do it, on local machine or on build server?
So, and again, let me try to answer in the right way. So, what I would recommend is to running at least before you cut the release branch. That's the most, that's the easiest way, because it's significantly time consuming, meaning that if your build time is, for instance, 3 hours, you can at least think double of the time, okay? So that's kind of the range. So double the time of your build, it's usually the amount of time it takes to run, and for this reason I would recommend to run it as soon as closer to the release branch.
Thank you for your presentation, for your talk. I have some questions, maybe they are too much C++ related, but let's continue. When you use like source code mutation, is it based on the C-lang from front end, or what is it based on? For example, you can just replace not equals with less, because less may be not implemented for this particular object, and you cannot recompile everything, and what happens under the hood. So
I cannot give you a very complete answer, because it's one approach that I discarded immediately, because it's the less recommended one, mutating from source code, and so I don't have enough experience to give you an accurate answer on that.
Okay, the second question was, do we change the source code of like only the main source code, or do we also change and mutate the code or the tests themselves?
I'm not sure I got to the question.
You have like the code which is like normal code, not tests, and you have tests.
Yes, we change only the source code, not the test. Tests are not mutated. That was the question?
Yeah. And why don't you mutate tests?
Because you want to evaluate the quality of the test. So you want to keep one part that is static, that is the test, and you want to see if the mutated code can pass through the test.
But maybe the test like is meaningless, and changing it doesn't make any difference. That's also sometimes useful, maybe?
Potentially, but I'm not aware of anybody tried to mutate the test rather than the source code.
Okay.
But it's a good question. I will search about it.
Okay, when you told that I need to recompile everything when I'm using bitcode, does it mean the static libraries, dynamic libraries I use?
Yes.
So I basically have to build from source and build everything from scratch, and like to completely redesign my current architecture if I'm using C++, and that might be difficult.
Absolutely, it can be very difficult. That's why I call it as a drawbacks. But you got it right. You have to compile from source. So all your dependencies, you must have the.
And why is that happening? Why can't it just try to like the code I have to recompile with this option, and the code which is in static libraries, like I don't actually want to mutate like JSON library I use, because
sure.
it's may be meaningless, because I try to use like
Absolutely, that's a great point. For instance, a JSON library, why I should mutate? It's not because you want to mutate data libraries. It's because to use the compiler flag to expose the bitcode, if all the dependencies are not compiled with the bitcode, the compilation succeeds. But then if you try to run mutation testing, you will get a 0 because nothing is getting mutated, because from all my tests, all the experimentation and all the practical things that we have done, Clang succeed, you build it, but you cannot explore the inner part of the code, and the mutation testing framework cannot inject the instrumentation code in every single method.
Okay, and maybe one more question. Do you have like a built-in into CMake to use this, not through a tool, because you were told that it would be great to have built it into your pipeline, and not having to run the external command after you compiled everything, done something? Do we have something in CMake?
Yes. Yes, we have something in CMake, and on our we use a custom pipeline, and in our pipeline we have a step that trigger exactly mutation testing and generate a report.
Okay, and maybe the last question. If
okay.
I have many of them. For example, if you like change something in your test and this gives you a crash, like undefined behavior, like segmentation fault, anything can happen. Yeah, what does your test suite do in this case? It stops, or does it try to run everything again?
It depends on the compiler, on the options that you use. There is a flag that is fast fail, then everything stop and fail, or otherwise keep executing everything, and then you will have one mutation score that is pretty bad. It's 100%, and you will probably look into what is going on, and instead of finding data about the test, you will find an exception that is recorded somewhere, and then you have to go back and understand what's going on.
Okay, yeah, thank you.
You're welcome.